Good evening, Rekha ma'am. Shall we start, ma'am?
Yes, sir. I welcome all. I welcome our guest speaker today, Mr. Sam Santosh, and all the participants for the second day FDP, a holistic approach for sustainable and smart agriculture using AI and deep learning techniques. Sir, good evening, sir. Thanks for joining. Now I request Shrikar to introduce our speaker to the participants.
Hey everyone, hope you all are having a nice day. Today we have with us Mr. Santosh Sam Koshi. He's designated as Joint Director. He has been associated with CDAC Hyderabad since 2005. He completed his PG DESD from CDAC Hyderabad and BE in Electronics and Telecommunications from Pune University. He has rich experience in designing and developing embedded hardware and software for a number of R&D projects at CDAC. His technological interests are Linux system development and device drivers, real-time operating systems, which are RTOS, and decision support systems, discrete electronic design, security engineering of embedded devices, and wireless communication. He is also involved in conducting training courses and technology workshops conducted by CDAC and in the area of IoT and embedded systems. He also delivered a number of talks in various conferences and workshops. He is keenly interested in the areas of technological inventions. So please, now I request our FDP speaker, Mr. Santosh, to kindly take over the session.
Thank you very much. Am I audible?
Yes, sir, you're audible.
Can you give me permission to share screen? Yeah. Okay. I hope my slides are visible.
Yes, sir, they are visible.
Okay. So let me quickly start off the topic of our interest today, which is the IoT applications in agriculture. I'll walk you through some case studies that we've taken up at CDAC in this area from the perspective of technology development and also its application in the field of agriculture as such. So my agenda for the day is I'll just give you a glimpse of what CDAC is, who we are and what we do. I'll talk about some of the potential applications that are in agriculture, where technology can help us improve productivity and also lead towards profitability. I'll glimpse you through some enabling technologies in agriculture and also overview the IoT technologies that are prevalent and specifically look at the WSN, wireless sensor network kind of technology. Following that, we'll look at the global scenario of things done in this area, the kind of applications that people implement, followed by the work we've done or I've been involved in this area at CDAC. And in summary, some IoT devices or some applications where IoT can be applied and some challenges that need to be addressed. So getting into it, about CDAC, we are known as the Center for Development of Advanced Computing. We are a scientific society under the Ministry of Electronics and Information Technology, Government of India. So we are a central government R&D research institute, autonomous in nature, but under the Ministry of Electronics and Information Technology of the Government of India. We have our presence in 12 cities as shown out here in this in the map of India, and we are headquartered at Pune. So I work out of the Hyderabad Center, which was started out in the year 99. And we are located in Hardware Park, which is our own premises. We have a main office building and hostel accommodation as well. We have a capacity for 200 engineers for work. We have state-of-the-art labs. We also have classrooms and student labs where we offer various skill-based training programs. So currently, our manpower size is about 150 engineers. 150 people, out of which we have about 130 engineers and some 22 non-technical admin support staff. If you look at some of the focus areas of CDAC, we have three major technology focus areas. They are in professional electronics, cyber security, and software technologies. Now, I work in the professional electronics group, and here we have two parts. The electronic system design and manufacturing group, which looks at VLSI, electronics repackaging, and some rapid prototyping and industrial design aspects. I focus in the embedded systems design group. So we work in areas like IoT, where we've applied the technology to agriculture, to transportation, and even smart city kind of applications. We undertake various wireless device development and application design kind of activities, and also have some strengths in the Linux kernel side, where we develop stacks that are related to networking and wireless comm and stuff like that. Now, we also have the fourth aspect of our center, which is education and training, where we conduct these PG diploma programs, which is more a bridge kind of activity, which tries to connect the industry needs against the academic outcomes. So students from the engineering stream are trained through diploma programs to be fit for the industry. That's one thing we look at. We also get involved in faculty updation programs, either by delivering lectures or even conducting various faculty updation programs. And post-COVID, we've also started the online training courses for engineering students, like an industrial training kind of setup, where students can join in and at self-pace can learn various kinds of technologies, like electronic hardware design for IoT systems, like blockchain technologies, and like mobile application development. So in a nutshell, these are the things that CDAC Hyderabad kind of works at. So let me now move on to our topic of interest. If we talk about agriculture, we just tend to think about it from a very technology agnostic or technology tough environment. Like we see very few interventions of technology in the field of agriculture, and it was not until the late 19th century that technology started making interventions into this space. So in the late 20th century, that is the 1980s and above, we had the genetically modified aspects that came into agriculture to improve productivity. Then we've had machinery that we see, tractors and various farm equipment, and to an extent GPS and stuff like that entering in to kind of mobilize the farm operations, the harvesting and the post harvesting operations. Now, the present state, we have a lot of varied technologies like weather modeling, like sensors, like drones and stuff like that, where a lot of data is being generated. And the problem is we can generate from a scientific term a lot of data, but unless that data can result into data insight, which can be given to the farmer or to the agricultural system, that data just remains academic or it remains scientific interest, but does not really meet a purpose. And so the future of agriculture, we envisage that various kinds of technologies like weather stations that are connected, like weather forecasting that comes in as an input, like the plant sensors that monitor and actuate various controls on the plants, and the drone, the UAV kind of technologies. All these will kind of uh, gather together or join together to create what we call the data insight, through which the farmer will be empowered to make better profit or better productivity in his field. So that we see as how technology has intervened and where it is going to take us in the future as far as agriculture is concerned. Uh, to just take this topic a little further, some potential applications in agriculture where such cutting edge technologies can lead to productivity and as well as profitability are kind of listed out here. These are not full, exhaustive, but they sizably cover a good set of applications where the technology has a role to play. For example, let's take yield forecasting and the market connect. Now, this is an area that is very interesting and important, both to the farmer as well as to the government. It is very tough for the government to know what kind of produce is coming into the market, so that they can ensure that a lot of produce doesn't come together at the same time at a specific market. What I'm trying to say by this is, we have these various mandis or markets where our produce goes and gets sold, or goes from the farmer into the market, and from there it goes to retailers. Now, what generally happens is, because we don't have very good technology support system at the field level, the markets generally do not know what kind of produce is going to come into that specific region, and so it ends up that many villages would have grown the same crop, and they are harvesting it at the same time, and there is a sudden outburst of these yield into the selective markets where the prices tend to fall and the farmer takes a beating in terms of the profits. Uh, Technology can kind of solve this problem if it can forecast the yield in advance, so as to allow the market to be connected and aware of what kind of yield is coming in, so that the farmers can be scheduled to send their produce to various kinds of markets and thereby also gain profit out of it. The other area is the crop or the soil health mapping and monitoring, where we know that if we are able to map the soil conditions, we will know what kind of crops to grow and what kind of fertility stake is there at the field, and therefore the kind of fertilizers that need to be input to the crop. Now, we know that fertilizers are a cost to the farmer, and if we can give the right kind of advice to the farmer, he will be able to improve productivity or the profitability, because his input cost reduces. At the same time, if we understand the health of the crop, we can best decide what kind of inputs the crop requires in terms of irrigation, or for that matter, even pesticide. Thereby reducing the possibility of over or under spray. Now, similarly, if we look at the farm weather monitoring, as of now, we always talk about macroclimate monitoring, where we look at the weather from a very high level. So we talk about temperature, we talk about the temperature above at one specific place, which covers probably a couple of kilometers or even more. We talk about rainfall, it is still the same, about 10 kilometers or so. The actual thing that is important as far as agriculture is concerned is the microclimate. And what is a microclimate? Generally, when the crop grows, it creates a canopy under which a new climate kind of is trapped, because the light enters in but cannot leave out, or the conditions within the canopy of the crop tend to be a little different. And the moment that happens, what we fail to realize is that the microclimate is actually stimulating certain kinds of pests or diseases to grow in a different form, while we are monitoring the macro sense of the weather. And this, therefore, with the use of microclimate sensors and stuff like that, we be able to understand what the plant is actually going through or the crop is actually going through to better regulate its inputs and improve its productivity. At the same time, we have the cases of optimal resource conservation in terms of soil, which is important, as well as water. We want to conserve these resources in a manner that they can be sustainable and they can be used in the future without spoiling the nature that we have, right? Moving on, an early detection of plant diseases or pest infestation is also a place where technology can help, because if we reduce the amount of pesticide that we spray, or if we are spraying the right kind of pesticide or the right kind of fungicide at the right time, it kind of helps increase in the productivity as well as becomes an input cost reduction to the farmer, which is an advantage. In addition to the crops that we talk in agriculture, there is a wide area of application also in terms of livestock and fishery health monitoring. These places are not away from technology. For example, fisheries do have, in a sense, some form of technology, but having more technology interventions into the space will help us to address the problems that these allied sectors face. As we move on and we talk about the enabling technologies, we can classify the enabling technologies that can enter into this space into three types. The first type is the data acquisition and actuation control technologies. Data acquisition is like sensors and getting information. Actuation control is some form of actuation where you can control sprinklers or you can control irrigation and pumps and stuff like that. So the popular technologies that are generally used in the data acquisition and actuation control space is IoT, which supports or helps in weather monitoring of weather parameters, precision farming, as well as actuation control. We can use drones. These are soft mechanisms or passive mechanisms of monitoring, where you can monitor the crop, you can monitor the soil, or you can monitor and survey, perform pest and disease surveillance. We also have autonomous robots and farm machinery, which are related to soil health information as well as actuation control. So in the data acquisition and actuation control space, these are the popular technologies that generally intervene. Moving on, in the data processing space, we have cloud-based technologies that are popularly coming up right now. And adding to the cloud-based technologies, we have technologies like big data, ML and AI, which is actually something that you guys must be listening to for the next 10 days or more. And also we have pest and disease modeling, NDVI, the normalized data vegetation indexes that can be calculated. We can do irrigation scheduling, soil health and yield estimations in the data processing section. So the data processing section is the place where all the data is housed, and models and various technologies operate on that data and come out with good advisory. Now, the third important aspect or the enabler in terms of the technology is data communication itself. Data communication pertains to two aspects. One is either the mobile-based communication technologies, which can be used for uploading data from the field or for disseminating information to the farmer or end users in terms of audio calls or SMSs for dissemination. Now, on the other hand, you can also use other forms of data communication like print media, like radios, like kiosks or web interfaces, through which the users can be intimated of certain aspects of their field or give information, ICT kind of information sharing with the end stakeholders. Let's move on to IoT technology and the overview of the IoT technology very quickly, so that it sets the stage or the tone for what we're going to listen as we go ahead. Now, how did we get into this era of Internet of Things? Begins with various paradigms. So in the first wave of computing, which we called the mainframe computing era, we are all aware that the computing infra was huge, and many users who could not afford that kind of a computing infra for various reasons would kind of log into these mainframe computers in a one-to-many architecture and perform their operations. So the genesis of these mainframe technologies was started by IBM with their System 360 system mainframe in the year 1964. So users therefore logged in through these remote terminals and they are able to users were able to log in through this remote terminal, and I think somebody is trying to annotate.
Yeah, sorry, sir. Once again, Dr. Sri Lakshmi ma'am, please check that your screen. You are doing some annotation on the screen. Kindly close it for some time. It is disturbing the speaker. Thank you. Sorry, sir, for the disturbance.
No problem. So this first wave of computing, as we had discussed, was the mainframe or the one-to-many, where many users would log into the mainframe and perform their jobs or actions. We moved on from the first wave of computing to the second wave of computing, which is called the personal computing. We are all familiar of this because we would have probably grown up and done our stuff in this era. And here, each one of us had a computer. These computers were connected to a bus architecture, and that's when the bus architecture kind of became famous and got instituted, where network switches were connected and the devices would kind of interact with each other over that bus. And this bus translated slowly into the internet, and we were able to communicate seamlessly from one end to the other. The third wave of computing, which we call the ubiquitous computing, is in a sense a many-to-one phase of computing, where one human is kind of surrounded with multiple computers. For example, if we think about ourselves, today we have smartwatches. This is a computer. We have mobile phones. These are computers. If you look at your personal home spaces, you have smart televisions, you have smart lights, you have smart refrigerators, you work with a laptop. And in that sense, a single user is now subject to multiple computers who are working seamlessly together to kind of provide them various kinds of services. Though in this current phase in time, we still see it disconnected. The purpose of these networking protocols and wireless communication technologies that are coming up is, in a sense, a wave which allows the technology to pervade into our spaces, but yet become seamless and integrate with each other to serve various purposes that we have. So, in a nutshell, these are many computers that serve an individual. These are smaller computers in terms of size, but they are much more powerful. Because if you look at the mobile phones that we have today and the kind of RAM and the kind of processing capability that these devices have, you would have never imagined about 10 years back that this could be the state of the art, where everything is kind of working on a mobile device. And not only does it be a computing era, this era also integrates various forms of sensing and actuation on board, so that you can monitor various conditions or various parts of your environment and take preventive or better action as per your convenience. Or the technology itself decides how convenient it can make the environment or conducive it can make the environment for us to have a healthy and a better form of life. So this third wave of computing was defined by Mark Weiser, the late Mark Weiser of Palo Alto Xerox, in the early 90s. And this kind of became the basis on which technologies such as the Internet of Things, which we talk about today, have started coming into the environment, into our world, and are seeing the light of the day. So what is the Internet of Things? this term, the Internet of Things, is an offshoot of the ubiquitous computing era and was coined by Kevin Ashton in the year 1999. From a Wikipedia definition, it defines the IoT as this: uniquely identifiable physical objects of everyday use and their virtual representations in an internet-like structure. So we have three keywords: uniquely identifiable. The second keyword is physical objects, that is everyday objects, bearing a virtual representation. So they have a virtual kind of a representation in an internet-like networking structure. So when we talk about these three terms that we referred to, we can summarize them to be object identification. The second aspect of this is remote monitoring, because they're physical objects, you want to know where they are. And if they are physical objects, you want to also perform some actions on them, let's say actuation control. And also, if you want to talk to them or you want to listen from them, you need a form of data communication. So in a nutshell, the Internet of Things, as I can put it, involves object identification, to an extent can involve, should definitely involve remote monitoring, and should definitely involve a form of data communication. The last term, actuation control, may or may not be required, but it is nonetheless an important aspect of the IoT definition as such. Now, what technologies enable the IoT? So if you talk about the object identification, we have technologies like the radio frequency ID. So this was the initial IoT definition which came into existence. So when probably 10 years back, when anybody talked about RF of IoT, they would refer to it closely with the term or RFID, right? They would say that RFID is a form of IoT. It only provided a form of object identification as such. Thereafter, technology moved on and progressed into what we call short-range data exchange, which is your data communication mechanism, through technologies like Bluetooth, near-field communication, and stuff like that. Going ahead, in terms of the remote monitoring and data access or data actuation kind of technologies, a very popular technology, the chunk of which we'll be talking today, was called the wireless sensor networks, which was actually introduced by UC Berkeley, or popularized. Let me not use the word introduced, rather popularized by UC Berkeley as the way forward or the future of the ubiquitous computing era. Now, what are wireless sensor networks? As the name signifies, these contain spatially distributed autonomous sensors that can monitor your physical environment or for physical environment for environmental conditions like temperature, sound, pressure, etc. And not only do they monitor, but they have the capability to even pass that information cooperatively between each other back to a place through a network where that data can be processed. So in simple terms, the wireless sensor networks integrated three different kinds of technologies on a simple substrate: the sensing and actuation technology, the processing technology, and the wireless communication technology. So if you remember, when we started debating or talking about the IoT or the technology enablers, we specifically use these three aspects: the sensing, the processing, and the wireless communication. Now we tend to see that all these three have been miniaturized in form factor and in power, and been brought onto small devices that can perform all of this together. And that is what the strength of the wireless sensor network is. So moving on, if you look at the general system architecture of any wireless sensor network, you have these wireless sensor network nodes or IoT devices, which are actually connected to various sensors. Okay, and not only are they connected with sensors, through which they can sense and also do some actuation if required, They have some form of processing capability. It may not be very huge, but they have microcontrollers or microprocessors through which they can perform a decent amount of processing. And also they are equipped with wireless communication radios through which they can transmit the data. And the moment I say I can transmit my data, I can also develop algorithms through which this data can be routed from distant locations to my destination. So that is why I said that these devices can cooperatively transfer the data through networks or through routing protocols back to a gateway, which will translate the backend network to a forend network. That is, one wireless protocol is translated into an alternate wireless protocol, and then that data, whatever data is sensed from the field, can be sent back to a wider range cloud or a remotely operated cloud where we can perform storage and analysis. So you can have a database, you can have some apps and kind of derive insight out of the data. Finally, the insights that are derived can be pumped back into the field to the farmer or to the end user or the stakeholder. So again, if you look at it from terms of the building blocks that these WSN systems have, we have data sensors, we have data processing, and we have data connection all together in the wireless sensor network architecture. You have the data thereafter reaches your destination, where you can use various technologies like the cloud computing, the big data, or the AI/ML kind of technologies to connect it to smart applications like smart homes, lighting, agriculture, energy, and stuff like that, and derive intelligent services through which your society or the system, your environment can be made smarter. So in that sense, the wireless sensor networks or the IoT technology becomes an enabler for various intelligent services that can be existing in our spaces. But when we talk about all this, there are certain aspects we have to think about. If you talk about the topologies in which these networks reside, they can generally form three types of network topologies: the mesh network topology, a star network topology, or a standalone network topology. So simply put, a mesh network topology is one in which every device can talk to the other device. Okay, so a device or an IoT node can become, in this orange color you can see here, the IoT node can end up becoming a kind of device that not only senses but also cooperatively participates in network formation and transmission of data from the remotest location to a gateway which is deployed on the field. Okay. Now, the moment you do something like this, what happens is you don't need a very high range wireless communication protocol, but these protocols require some form of processing routing capability so that they'll be able to send the data to a gateway and from that gateway to the cloud. So this is one form of communication. The second topology. The second topology is one in which these devices don't form networks on the field, but they are a kind of a star architecture where they are individually connected with the gateway, right? So what this does is, if you have a good range protocol, a decent sizable range protocol, communication range protocol, these can become autonomous devices or sensors that can talk independently to a gateway which is deployed a little further away, and therefore reduces the number of devices that need to be deployed in the field. The final or the third is just a slight increase in terms of the network capability of the device, which is called the standalone architecture, where the device per se is an standalone entity of itself, which does not require a gateway. So the gateway is basically a network translator or a protocol translator. It changes one protocol to the other protocol. And therefore, in these standalone architectures, the communication can directly talk to the cloud. So you don't need a gateway. And these devices are fully autonomous or fully standalone to communicate back to the cloud architecture. So this is various forms of network topologies that persist on a IoT space. Now, what enables this kind of a technology showcasing is basically the kind of wireless connectivity spectrum we have that falls under the IoT space. So we are all aware of Bluetooth, the IEEE specified by the IEEE 802.15.1 MAC and 5. We were all also probably heard about Zigbee, which was using the IEEE 802.15.4 standard. And these were the prevalent technologies that were generally used for IoT or wireless sensor networks. Now, these operated in 2.4 gigahertz frequency spectrum, where they had a range of kilometer, probably a kilometer. The problem was they had some decent data rates, as we can see here, up to 3 Mbps is what the Bluetooth talked about, and the WPANs, or the low rate wireless personal area networks, on which Zigbee falls, was around 250 kbps. The power consumption was nonetheless low, but only thing was the range is not very good or very feasible for wide applications. Now, understanding that the frequency of operation also is an ISM band, and therefore becomes an inhibition in terms of the range that can be achieved for the given power and data rate. New technologies in the sub-gigahertz space, like LoRa, NB-IoT, Sigfox, and Weightless, all these technologies kind of emanated trying to provide range for several kilometers. So in general, they begin from 5 kilometers of communication to all the way up to 15 to 20 or even 50 kilometers, depending on the kind of technology that is used. Now, obviously, there is going to be a compromise. If you're having very good range and low power consumption, the compromise that you're getting is in terms of the data rate. So the data rate would generally fall to about kbps, where you can transfer very small amounts of data over large periods of time, over large distances. So in general, when you're talking about the wireless communication space, there is a trade-off that happens across these 4 parameters: the operating frequency, the range, the data rate, and the power consumption. So going ahead, we have the other high data rate communication technologies like Wi-Fi, 2G, 3G, or the 3GPP standards, the cellular band technologies. So where you have good range, you have good data rate, but at the cost of a power consumption that is generally high and not useful for outdoor deployments or devices that need low power consumption. So when we talk about this kind of an aspect, everything has a catch, or everything comes at a cost. And so what are the key considerations that we need to make when we think about developing an IoT system? The first is in terms of the power consumption, because these technologies, based on the network topologies that I've shown, could have multiple devices. That is, you could have end nodes like sensor devices, you could have actuator devices, you could have router devices based on the kind of network topology, and you could have gateways. Some of these architectures need gateways, some of these architectures do not need gateways. So the overall network power consumption will vary based on the kind of device architecture you use. And so the system and network architecture, therefore, is highly dependent on the kind of power consumption that you're going to have and what kind of environment in which that system or network architecture has to be deployed. That is the application environment. The second aspect you also have to think about is the battery-based device architectures. Simply because if you want to think about these devices to be deployed in fields or outdoor environments for long term, where you don't have adequate sources of power supply, you have to think about the design to be such that they can last on battery, or they can have some forms of energy harvesting through which they'll be able to sustain for a long duration of time. So I can have a mobile phone that gives me whatever features I want in terms of processing power, sensing, and stuff like that. But the problem I will find is that I cannot use this mobile phone for a long time because I need to keep recharging the battery, right? So if you're trying to put a mobile phone kind of an application in a field where you need even 1 watt or 5 watt of power consumption, it's going to be a mammoth task. And so your energy, your consumption has to be thought about from perspective of what kind of application your device is going to be deployed at. The third aspect is your deployment and the networking requirements. The moment you say, I want to put a device in a field, you should definitely have remote access where you can configure the device to perform in a certain way, and the device should be able to manage itself in that network to a sizable quality of service. That is, it should not lose communication very frequently, and you should at least have windows of communication with the device so that you know what is happening on the field. For example, if the communication fails, you won't know whether the device, something has manually happened to physically happened to the device, or whether the communication itself is a problem. So you should have packet or pockets of windows through which you can communicate with the device, or alternate sources of communication with the device through which you can keep in touch with it. The second aspect is packaging, especially from the perspective of outdoor deployments. It rains, there are various temperatures that you have to face, or if this device has to be put in an industrial environment, there are vibrations, there are noises, there are temperatures of varied degree that have to be sustained. So the packaging also becomes important. Thirdly, your deployment cost should not be sizably higher than the cost of the technology itself. And fourth, it should be easy to deploy. It should not be such that you need an engineer to stand on the field and go ahead deploying the system. So that's another consideration you have to think about whenever you're developing the IoT application. Fourth is the coverage area. What kind of range are you going to get with this device? What kind of sensing sensitivity are you going to get with this device? What kind of accuracy you need? And those aspects, all defined by the application domain. The architecture should support large number of devices because the IoT talks in billions of devices. And so your network architecture or your device architecture or your system architecture, all of this should be scalable so that large number of devices can be integrated into that application. And more often than not, you have to think about standalone operations so that you don't have to send a person to the field. If there are any teething issues, the network and the device should be able to recover by itself. Last but not the least, the most important aspect is the device cost, because if the device cost is prohibitively high for the technology you're using and the application domain where it's being deployed, this will not sell. And so when you're making an IoT system, these are various aspects against which you'll have to evaluate to know whether the system is going to sustain or the system is going to become a useful entity in the field. So now we look at what is happening globally in the space of IoT, especially from the agriculture space. You can look at this device, which is called, which is created by a company called CropX, a US-based company, which is nothing but a soil moisture, soil temperature, and electrical conductivity measuring device. So the sensors are kind of embedded into this probe out here, and then you can just take it and plonk it into the field or insert it into the field, and it has its own wireless communication mechanism. So this is able to measure the soil moisture and soil temperature while also checking the electrical conductivity or the salinity of the soil. And it is able to send that information to a remote station where the irrigation requirements of the field can be addressed or can be advised. In terms of the cattle monitoring and management application, Afflex and Kohler, these are companies that use some agriculture sensors like collar tags that are used to that can be put on the leg or on the collar of the animal, and so it tracks the position and the temperature of the animal, especially when it's in heat, so that it can deliver and various health related aspects of the. It can monitor the health of the livestock. So where it grazes, what kind of nutrition it's getting, all those kinds of aspects can be monitored. This is another interesting application that we've seen from a company called Veris, which is a robotic and farm machinery equipment that just connects to a tractor. So like a tractor implement, you can connect this device. And as the tractor moves through the field, this device surveys the field in real time and assesses the electrical conductivity, the organic matter, and the pH aspects of the field. Now, using that information, you can perform a soil mapping of the field, understanding what kind of nutrient or intake the field has, and thereby kind of creating soil health maps or supplementing the data in the soil health map. Now, what other kind of applications do robotics and farm machinery bring onto the field? They bring weeding robots, harvesting robots, material handling robots, sowing and farming practices, and stuff like that. Drones are popular technology. We're all aware of it and also a lot of interest. Two aspects of the drone are interesting or unique to the agriculture space. One is in terms of the payload, where in addition to your RGB cameras or your normal cameras that you use on a drone, specific cameras like payloads like thermal payloads, multispectral payloads or hyperspectral payloads are also finding applications in the drone devices. And using these drones, you can do a passive kind of surveillance or scan of your field to advise or to cover larger areas for applications like irrigation, pesticide attack, or the nutrient aspect of your plant and farm. This is another interesting device, which is called the POC, which just integrates onto a farm device or a machine or the tractor, and it collects your field information and generates what we call as electronic field records that help you to know what is the state of your agriculture field. So it's just a data collection logger or a data acquisition logger that collects data from various aspects of your device, like the seeding, like the harvesting and other plant kind of information, and tells you the status of the field. This is a web-based application that allows you to connect your sensors or your devices from the field and see their performance in real time through a online dashboard kind of application. And using that, you can run decision support systems or application models to make sense of your data and throw insight out of the data that is being generated. Now, quickly moving on to what we've been doing at CDAC over the past 10 years in this area, in the agriculture space. I've been personally involved in the area of IoT in agriculture, and we've executed a few projects, R&D level projects, but two of these I'd like to talk about from the IoT space. One of which it is called the Harita Priya system, which was a groundnut pest and disease forewarning system. So for the groundnut crop, we were undertaking pest and disease forewarning and also irrigation scheduling. So I'll talk a little bit of detail about what we did in this application and how it benefited the pilot space. The second was an enablement of the scientific community, where we used the technology.
Sir, excuse me, sir. Sorry to disturb you, sir.
Sure.
Do you want any break, sir, for 5-10 minutes?
No, I'm okay. If the participants need a break, you can just tell me. I'm okay to continue, but if you all need a break, you can just tell me.
No. Okay, sir. You can continue, sir. No problem.
Okay, sure.
Okay, sir.
Yeah. So the second part of the case study that I'll just quickly run through as part of this talk is the way in which we were using the technology to enable the scientific community, especially the agriculture research institutes, to develop models through which disease can be forewarned. disease occurrence can be forewarned. So we worked with the Indian Institute of Oilseeds Research to develop a castor grey mold disease forewarning system. So the first project is more an application of the technology, assuming that we have models to send advisory to farmers. And the second was the enablement of the scientific community themselves in using the technology to develop the models per se. So moving in, the Harita Priya project, it's an IoT-based end-to-end solution which can provide agro advisories to farmers with three major components. The first was the wireless sensor network system, which should be robust because it has to be field deployed. It should be standalone because they'll be remotely deployed. They should work by themselves. And it should be able to gather real-time climate information, especially microclimate information from the crop canopy of the farmers' fields. So this is a technology that has to be deployed in the farmer's field, where it has sensors connected to it, and it can be put within the crop canopy so that the microclimate can be assessed. And once the microclimate data is received, it should be able to communicate that data back to our servers. So that was the wireless sensor network technology. The second aspect of the technology development was a decision support suite of tools or models that allowed groundnut crop management practices for pest and disease or irrigation scheduling. That is, these decision support models are the outcomes of agriculture R&D, the research institutes, who spend a lot of time trying to characterize various pests or trying to characterize various diseases to see how they grow. And one important aspect of the growth of pest and diseases is the fact that these are stimulated or these are caused to grow much better based on certain ambient weather conditions or climate conditions. Okay, so these decision support models were available from the agriculture research institutes through years of research. And our job was to take some of these models for certain pests and diseases and for irrigation scheduling and implement them in an IT infrastructure that could use the IoT data or the WSN data and perform the analysis of the sensor information. Third, once we get the models and the models feeding off the sensor data, we should be able to provide location specific and personalized agro advisories to farmers in their local language. So location specific means it should be very specific to the area in which the device is deployed. Personalized means it should be pertaining to a specific farmer and the problems that his crop is facing. When we say agro advisories, you know that the agro advisories are some forms of advice that we tell the farmer about the state of his crop, and that should go in the local language, which is Telugu, which we were trying to do as an advisory through SMS to the farmer. So as far as the technology that was implemented is concerned, for data acquisition, we use WSN, or wireless sensor network. We had 3 devices that were deployed in the field, 3 types of devices, not 3 numbers, but 3 types of devices that were deployed. The first is a canopy sensor unit, because we said we want to sense the microclimate. So this was a device, an electronic device that implemented a protocol called SDI-12, which allowed it to communicate over the UART interface with an end node, WSN node. So the canopy sensor unit, kind of as its name signifies, sits in the canopy, has sensors interfaced to it, and uses a form of communication, a serial form of communication using SDI-12. Now, this canopy sensor unit is connected to a WSN node, which has a wireless Zigbee-based communication associated with it, so that now this two are homogeneous in nature, the WSN node and the canopy sensor unit. And this entity can wirelessly communicate to a distance of about 300 meters in a single hop communication. The gateway was therefore deployed at one point in the field, which had two kinds of radios. We had a ZigBee front end, which was talking to the IoT node or the WSN node. And we had a 2G or 3G, 4G backend, which was communicating back to our remote server, which is deployed in Hyderabad. Okay. For the data processing part of the technology, we use various web technologies where the decision support forewarning models were implemented. And these forewarning models, as I said previously, were applicable for pest and disease forewarning, as well as irrigation scheduling in the groundnut crop. We used some data processing technology to generate the advisories in local languages, that is Telugu, and also used a map-based web application through which you could look at the field and know the status of the devices in real time. As far as the communication is concerned, we use mobile communication where we were uploading the weather data from the field using the 2G, 3G communication, while we were using again the SMS gateways to kind of send out SMSs to the farmers in local languages. So the system architecture is exactly similar to what I had described previously. In terms of the technology, the WSN unit had these three devices. The canopy sensor unit, where sensors were interfaced. So if this is the crop, we had about 5 sensors: temperature to measure the microclimate, relative humidity, again to measure the microclimate in the crop canopy. We had a sensor called the leaf wetness sensor, which was developed in CDAC, which measured or replicated a leaf and the wetness that the leaf was assessing or monitoring or experiencing throughout the day. And soil moisture and soil temperature sensors, which would be deployed subsurface so that we know what kind of irrigation requirements are needed by the crop. So these 5 sensors were connected to the canopy sensor unit. And from the canopy sensor unit, we connected this serially to my moat or the WSN node, which had the ZigBee wireless communication. Now, because this entire architecture had to be deployed on the field, this device entirely had to be powered by a solar powered circuitry. So we had a battery and we had a solar panel and the charge controller circuit and stuff like that to ensure that this whole system would homogeneously function as one unit on the field when it is deployed. So this is how the canopy sensor unit would look like in the field. So you see that we have a device here, electronic board circuit inside, which has a sensor. So this is the leaf wetness sensor that you can see out here. We had the temperature relative humidity sensor that is deployed in this gill radiation shield. This gill radiation shield again was developed in CDAC ourselves, and all this architecture of the canopy module itself was developed at CDAC. And the soil moisture and soil temperature sensors that were kind of sent into the ground. You can see here a cable that's going into the ground where the conditions of the field were monitored. This electronic board was a PIC-based 8-bit microcontroller, which just had some bare metal firmware written on it. There was a protocol called SDI12, which allowed us to communicate with this device from the moat or the IoT from the WSN unit. And third, this was actually powered from the WSN node directly. So as I already mentioned, we interfaced this to 5 different sensors. Now, these sensors are generally purchased off the shelf, but the leaf wetness sensor is something we developed in CDAC, and the radiation shield for this temperature relative humidity sensor and its supported electronics has been developed in CDAC by ourselves. That canopy sensor unit talks to the WSN node or the WSN unit, which is again hardware that is indigenously developed in CDAC. And this hardware had 2 types. We had a MSP 430 based hardware as well as a Cortex level hardware. Now, at that time, we were running an operating system called TinyOS on this WSN node, which is an embedded operating system developed by UC Berkeley. And we had a mesh networking algorithm with some low power scheduling algorithms and the SDI12 interface driver for its processing. This device was again solar powered. The canopy sensor device was powered through this device, but this device per se is solar powered. And we had a sensor interface board through which you can plug and play various sensor devices or even have physical sensors connected to this device. This device had a ZigBee communication as far as the wireless comm is concerned. And you can see an antenna out here on this device. So multiple such kind of architectures can be put onto the field where they can wirelessly communicate. Now we package this device for outdoor deployments with standardization of ingress protection 67 to ensure that water does not seep in during rainy conditions. The third device in this architecture of data acquisition is the WSN gateway, and this is how it looks like. So there are two antennas, as you can see. One antenna is ZigBee based, so you can talk to the front end network, and the other antenna is a GSM based antenna, which talks to the back end network to upload the data. So the gateway is basically a protocol translator. It collects information or data from various sensors or WSN units deployed on the field. So in a field, there'll be one gateway, and it collects the data from all these sensing units. And once it receives the data, it will translate the data into a GSM protocol format and upload that data back to the remote stations. So the software and hardware were developed at CDAC. We used a Cortex M3 based microcontroller, which was ultra low powered in terms of the hardware architecture. We had a base station, which was deployed there for the front end reception from the deployed nodes, the ZigBee side. And we had a GSM modem kind of hardware that allowed us to send the data back to our remote station with solar power conditioning circuitry built in-house. On the software side, we had implemented the Kucox real-time operating system. It's again an embedded operating system with a little more features that can run on the Cortex M-based series of processors. And we had local storage so that if you don't have network connection, you can still have the data. We had power management techniques through which we could send this device into long sleep cycles when data is not available or not required to be sent, or we want to conserve the RF communication. And we also had HTTP based upload functionality where through XML we were able to send our data back to the server. So how did this device span? It was able to operate for 48 hours on the field by itself without sunlight. And on an average, the device would consume about half a watt of power with a peak consumption whenever transmissions happened at around 1.5 watt. And this was again IP certified, customized for all outdoor weather field conditions of deployment. So this is how the field deployment would look like. This is the WSN unit with the canopy sensor unit in the field deployed in a farmer's field. And here's my WSN node that wirelessly communicates. And so in a given village, I can have multiple such kind of nodes that are deployed at different locations, and they form the network, and they're able to communicate their data from their respective locations and send it back to the gateway. And at the gateway, we'll receive the data and send it to our servers, which were residing in Hyderabad. So now this application per se was implemented in Anantapur of Andhra Pradesh, where groundnut is a major crop that's taken up. We had deployed about 74 of these IoT nodes in 5 villages. So every village would have one gateway and multiple set of nodes. So in some villages, we had 8 nodes to all the way up to 20 nodes with each with 5 sensors deployed there. The total area we were covering was about 450 acres. and we were able to integrate some 700 farmers into the system to send out some advisories to them. So these are the location or the villages in different agro climatic zones of Anantapur region where this technology was deployed. So as far as the decision support practice was concerned, we had targeted the groundnut crop. This is how the groundnut crop looks like. We implemented the decision support models for generating forwarding alerts for disease and pest monitoring. So we had a model called the leaf wetness index model for a disease called leaf spot in groundnut. So if you see this leaf of the groundnut crop, it develops these diseases, which is called the leaf spot disease, where lesions of brown to black spots cover the leaf and reduce its chlorophyll generation content capability, and thereafter thereby hampers the production or the growth of the pod itself. We also had a a pest, which is called the leaf miner pest, for which we were using a model called the growing degree day model, which was temperature based, to kind of forewarn the occurrence of this pest. Now, this pest is pretty smart. The adult would lay its eggs on the leaf. The eggs would hatch, the larva would come out, then it will use the leaf to cover itself and pupate, after which it again becomes the adult and flies out of it. So if you don't detect this in time, even after spraying pesticide, the pesticide may not enter into the leaf to damage the larva. So the growing degree day model would allow us, therefore, to know that this larval stage is occurring, when it is occurring, and when the next generation of larval stage could occur, thereby allowing us to take preventive action. We also had a model for irrigation scheduling to tell the farmer when irrigation is required. Now, once we have all this data coming into the system through various sensors, the models would feed on the data and generate advisories or alerts. And then based on those alerts that are generated, we would transliterate, we'd use that alerts to generate advisories to farmers and send it as SMS in local languages. So just what I mentioned here, the WSN nodes end up sensing the microclimate at the crop canopy in a real-time basis. From the canopy, we transfer them to the transmit that data, the sensing data, to the gateway, which has a SIM card and a modem connected to it. So it kind of transmits that data back to our remote server. The servers were deployed in Hyderabad, so we would run decision support models on that server for the data that was received from the field. And those decision support models would generate an alert, which some expert would be sitting and look at that alert, and based on the farmer and his crop, he would decide what kind of an advisory was relevant, and he would type out that advisory in transliterated Telugu, which would generate a Telugu message and send it out to the farmer at his field. So this is the web interface that we had developed for the application. So you can drill down to it's a map-based application. So you can drill down to the various nodes and see its current state of life. So the green, as you can see here, are all the nodes that were deployed in this village at some site. And the red one would indicate that the device has not been working for a week for some reason or the other. Now, not only that, we had an interface through which this kind of an interface where the alert would be generated in English. The agriculture officer could sit, look at who the farmer is, when was his crop sowing date, did we send a previous advisory to him, and based on that information, type out an advisory and just click a button and that would go out to him in Telugu. So we enabled the system with 4 types of advisories. One advisory that was based on the alert that was generated by the WSN system. One advisory called the scheduled advisory based on the body of information or the body of knowledge that the agriculture research institutes have developed a package of practices that could go out to the farmer at regular intervals to keep them engaged. A specific advisory that we could send out to the farmer for his specific crop if the agriculture officer had some information to share. And finally, a general advisory that would go down to all the farmers, telling them this is some announcement that the department would like to integrate or communicate with them. So this is how the messages would go onto the farmer's website and farmer's mobile phone. And we had a database of all the 710 farmers, and specific to him, specific to his crop sowing date, specific to his field and the problems of his field, we were able to issue out some advisories to the farmer. So this is what I kind of load up in terms of the advisory. So the system will generate the alert on a certain date. This was done in 2015 to a certain farmer, and you know when he has sowed his crop, you know what is his previous advisory, and so you can select the farmer details, type up the message out here, and click this button for it to be transmitted to the farmer in real time. When we did this pilot, we ran it for 2 seasons. In the Kharif season, that is the rain fed season of 2015, we were able to deploy this in 3 villages where only 117 farmers had taken sowing that season. During that season, our WSN system generated about 41 alerts, and those alerts were converted to advisory, and we were able to issue it out to the farmers. Now, since then, we ran this for a year, for 3 seasons, the Kharif 2015, Rabi 2015, and Kharif 2016. And we were able to issue out in that season about 561 alerts to the farmer to keep them engaged. And as on date, that is still those 3 seasons, about 3,500 plus advices were issued out to the farmers. So what we realized from all of this is the technology intervention is something that can happen in the field. You can generate advisory and send it out to the farmer, and it's a good way of engaging the farmer, keeping him notified with scientific information that tells him that the state of his farm is in this sense, and what steps he has to take to improve his yield. So we've published a couple of papers also on the work that we've done out here. And this is just a snapshot of what my entire team in the field setting up these devices all by ourselves. So yeah, this technology received a couple of awards, the Smart Technology Award of Scotch in 2015, as well as the WSIS, the ITU International Award for a smart intervention in the area of ICT in e-agriculture. So yeah, so that was the first case study of an IoT application for a pest and disease forewarning model and irrigation scheduling model that was deployed in the farmer's field. The second is more a scientific enablement of the IoT system for the scientific community, where we were looking at the castor crop for a specific disease called the gray mold disease. And the intention or the objective of this project was to develop a disease forewarning model for the castor crop using the IoT data. So our partner in this was Indian Institute of the Oilseeds Research at Hyderabad. We had deployed 4 WSN gateways or IoT gateways, 12 nodes, and 24 canopy sensor units. Each node had 2 canopy sensor units with these 3 sensors: temperature, relative humidity, and leaf wetness. And for 3 years, we ran this, collecting data from the farmer fields from 4 different locations in different parts of Telangana. And we were using that data to generate a model. So if you look at the deployment sites, one deployment site was at Rajendra Nagar in Hyderabad, where we had a poly house where the technology was developed, so that we could perform controlled experiments with the fungicide and see what kind of temperatures stimulate the growth for the model development. Apart from that, there were 3 villages, one research station and 2 other villages where the technology was developed in a 1:3 ratio, 3 nodes and 1 gateway. And each node had 2 sensors with the 2 canopy sensor units, each with 3 sensors. So this was kind of architected in the field, and we were collecting data for this. So this was done in Telangana region. So here is the Hyderabad location where it was deployed, and here about 12 nodes in Mehboob Nagar of Telangana, where the experiment was performed. So just the real-time information of one of those farms and the data associated with it. So coming very quickly to the summary of what I've been talking so far. How does this IoT technology help in agriculture? You can use the IoT nodes for data acquisition and actuation control as one of its major strengths. And this data acquisition and actuation control leads to various applications like microclimate monitoring. You can use drones, which again have sensors or payloads like multispectral or hyperspectral applications, and then use that data for AI/ML kind of deliveries. You can also use IoT in a form of robotics and autonomous field machinery, which is prevalently important for soil mapping kind of applications. How is this useful? You can think about irrigation, you can think about fertigation, you can think about pesticide control in your field. Some of the potential applications, as we discussed, you can use the IoT and drones for multiple crops and for multiple management practices. We did it for groundnut and castor, but sky is the limit pertaining to the number of crops we have. You can use it for multimodal data fusions. You can fuse data from IoT, you can fuse data from drones, you can fuse data from farm machinery and lead to better decision making. You can use these technologies to identify crop signatures, like what kind of crop is growing and the cropping patterns in a given state, in a given district, what kind of cropping patterns are being followed, and use that to come out with yield forecasting models that can connect to the market, which I had initially discussed. And therefore, yield estimations can be done, market planning can be done. You can base it on coverage and plant health. You can use these technologies for plant disease surveillance or pest and disease surveillance, for plant health, for soil health analysis, for livestock fisheries, and for development of health maps, plant health maps, weather maps, and stuff like that. All said and done, though I've probably painted a very rosy picture of the technology per se and what we've done, there are challenges and probably some solutions to take it forward. So if you look at the IoT side, I'll just talk about the IoT or the device side to start off with. First of all, you're talking about wireless communication. And so there should be a reliability in terms of that communication data. And this reliability is in terms of the amidst the crop foliage, that is, even after the crop covers it, the range should be reliable. So based on the kind of frequency, there is a lot of absorption that can happen in the field. Based on the kind of rainy conditions, there could be a lot of loss of packet. Finally, there are times when you just can't approach the field. And so the last mile connectivity issues lead to some communication reliability problems. Not only that, on the communication side, you have to think about the range, the power consumption, and the data rate, because there's a there is a trade-off across these 3 parameters. So if you want a high range, it could be based on either high power or low data rate. If you want a low power consumption kind of application, you may have to compromise in terms of the data rate to be low, and sometimes even the range to be low. If you want a high data rate kind of application, it may have a trade-off with a high power consumption and may result in a low range. So you have to balance between these various technologies. These are the challenges that generally we'll face as we think about IoT kind of technology for the agriculture applications. What is our way forward? Rather than looking at gigahertz radios, or reduce the frequency. So lower frequencies, higher range. That's a sub-gigahertz radio. Review your network topology. Try to put the devices as much as possible into sleep, where you consume power, and use large range kind of communications. So you move from a mesh topology to a star topology, where you can save a lot of power, and migrate to these LPWAN technologies, which give you lower data rate because you don't need too much of data coming from the field, but you have a good range and you have good power consumption on the field. In terms of the deployment, your deployment should not be, there's a challenge of it being laborious because of multiple device architectures or device types. You saw that in my architecture initially, we had 3 different types of devices, and that makes the deployment a little tough. And also, this is inhibitive to the field operations. So if I put such a big pole in the field, if I'm moving a tractor, that becomes very difficult to operate. So when we did the technology deployment in 2015, the environment was not conducive to miniaturize, and other wireless protocols are not conducive to miniaturize and come with better rugged infra. So going ahead, the challenge would be to look at plug and play kind of architectures where it's standalone. So the farmer can plug the device whenever he wants into the field, and when he's doing operations, he can remove it and then take it away, perform his operations, and go and replug the device into the field. So again, look at star topology, invest in high range so that you don't need too many sensors on the field. Third is cost benefit. We all know that these are electronic technologies, and looking at our farmers and the land holdings, which are small and marginal, this technology per farmer is prohibitively expensive as on date. Though we've indigenized the technology and brought it down to probably 1/5, it still is costly for a farmer to afford. And so we have to look at models where this becomes more acceptable to the system. So what we propose generally is to look at representative data. That is, rather than having multiple devices in a village, just have 2 or 3 devices that are representative of that entire village. Build up community-owned insurance models, like the insurance model, where you subscribe or you ask for only the data without having to cost. You pay a premium, buy the data for a season without having to worry about the technology cost per se. And the moment we think about mass manufacturing or corporate farming, the cost will definitely come down. So, for example, if I have to invest 1 lakh in a village and I have, let's say, 50 farmers, that 1 lakh for a period of, let's say, 3 years can come down to as low as 100 rupees or 200 rupees if I increase the number of farmers and scale it up to the for 4 villages around the place where it is deployed. What would happen is then I would lose in terms of the scalability or accuracy aspects, because now I am taking one representative data or 3 or 4 representative data from a village. And so it's a matter of whether you really need a fine-grained accuracy or even a coarse level of accuracy is good enough. And as far as the IoT system is concerned, we feel for an Indian context, a village level granularity is a good precision as far as the country is concerned in terms of the cost benefit as well as the deployment possibilities. Some other challenges that we'll have to work through for this to become a reality is the dearth in terms of the models. We need to enable the scientific community with these kinds of technologies to develop much better models that can be real time, that can address the challenging needs of the agriculture field. We need to create success stories that are field tested, reliable, and dependable. These devices have to be field deployed. They should work for various types of climatic zones, agroclimatic conditions. The models should support them. And so these devices should be rigorous in terms of the testing should be rigorous for multiple crop cycles before we can actually build a business model around it. The other aspects are in terms of the social stigma and the melted block towards acceptance, because people are used to a certain traditional form of agriculture, and pervading into their mind space is something we have to address before this technology can be useful. Finally, when you talk about communication and technology, the silent underbelly or the technology that's all generally overlooked is the network security and sensor development that is paramount important for this kind of technology to really see the light of the day, because we don't want such kind of technology to enter into the field where it becomes a weak link into major systems and then creates hazards for our food chain and global supply. So network security is very important as much as is the sensor development, which is required on an indigenous scale in the country for this technology to be really useful. So what actually this requires is a pan-India level multi-institutional collaboration, including various stakeholders. We should have focused projects with rigorous field testing, and we should build up these success stories using complementary technology interventions. So I think this is it from my side for today in terms of the IoT space. I hope I've been useful in what I've delivered. I think I'll stop for now. If there are any questions, you can kindly let me know. I'll be willing to answer. Thank you.
Thank you, sir. We will have a question and answer session. Participants, if you have any questions, you can raise the hand. We will unmute, or you can put it in the chat. Yeah. Yeah, there is a question. There is a hand. Yeah. Prasad, sir, you can continue with your question.
Good evening, sir and ma'am. Very nice presentation. I'm very happy to learn so many things. I have a small doubt. But, you have mentioned that sensors and actuators. What is the difference between sensors and actuators?
Yeah, so a sensor is a device that allows you to monitor. For example, if I say there's a temperature sensor or a leaf wetness sensor, it will tell me the temperature at that place. So I'll just get information. Okay. When I say there's an actuator, I can control a certain operation. For example, if I have a pump, I can using the actuator, I can turn on or turn off that pump. Okay, so sensor is a passive device that receives data, and an actuator is an active device through which I can control. I can turn on a pump, I can turn off a pump, I can turn on a sprinkler, turn off a sprinkler, or turn on the AC, turn off the AC. So any operation of control can be done through an actuator. I hope I've answered your question.
Yes, sir. Thank you so much for this answer. Sir, for leaf wetness, how we measure that leaf wetness, and for soil moisture, soil wetness, for irrigation scheduling, how it is helpful? I mean,
Yeah.
both are different.
Yeah, so leaf wetness per se is only generally used for disease monitoring. Okay, so leaf wetness is nothing but a moisture sensor put in the field where you can count the amount of time the sensor is wet. Okay, we know that when it rains, the sensor gets wet. We know that if there is humid conditions, the humidity can condense and the leaf can get wet. We know that if there is dew conditions in the field, the leaf can get wet, right? So if I put an electronic device in the field that can monitor this wetness, even though it does not touch the plant, what I'm able to know is how long there is wetness in the field. And that wetness can be correlated to the growth of a disease, which is what we were trying to do. That's about the leaf wetness sensor. Coming to the soil moisture and the soil temperature sensor, the soil moisture temperature sensor, there are multiple ways in which soil moisture can be measured. For example, we were using a gypsum block soil tension sensor, which had gypsum as one of its major elements. So if the moisture is high in the surrounding, the gypsum would absorb that and a change in resistance could be detected. If the sensor is wet and the surrounding is dry, the gypsum sensor will give away its moisture, and that loss of resistance could be measured. So that way you calibrate it to the moisture content. Other technologies are also there, like the TDR, time domain reflectometry, frequency domain reflectometry, and capacitive kind of sensors, which can be deployed in the field to measure soil moisture and calibrate it to a certain to the moisture level. Okay, the electrical parameter will be resistance or capacitance or time or frequency, and that is calibrated back to the moisture content. Now, soil moisture per se will tell you whether you need water or you don't need water. But how much water you need depends on the crop intake, the soil data, as well as the ambient temperature conditions or the soil temperature conditions, know how the water is evaporating from the field. So combination of all these sensors with a model will allow you to develop a irrigation scheduling scheme for the crop.
Yes, sir. Thank you, sir. Sir, which model you are using by all kinds of data you have collected by the same, sir? Then which type of model you are using for giving decision?
Yeah, so we for the leaf, we were looking at a disease called leaf spot, which we had a leaf wetness index based model developed by some university abroad and researched by Equisat also over here and CRIDA. We use a growing degree model for pest and disease, pest forewarning, a leaf miner pest in groundnut. And for irrigation, there is a model using the aerometer sensor based on soil tension that the vendor of the sensor provided. So we were using those models for our implementation. But as far as the oilseeds research project was concerned, we were generating data to use that data and correlate it with the disease and come out with a separate model. So our model was based on temperature, RH, and leaf wetness.
Okay. My last question that you have mentioned in some abroad places, you have some ideas that soil mapping, how it is done by using instrument in the field level, soil mapping of nutrients.
Okay, so frankly speaking, soil mapping is done in a rudimentary way through lab tests. Okay, there are very few companies which develop sensors that can be deployed in the field. Okay, that is a gray area. It's a potential application, but we don't have enough kind of technology that can readily go into the field. On a prototype basis, people have done some form of research for nutrient sensors, for other kinds of sensors, but in general, based on the parameter nutrients, we don't really have many devices. For electrical conductivity, we have some devices. For soil pH, we have some devices, and for organic matter, we have some devices. So it's a gray area. There's a lot of work that can be done in this area, but it needs material science collaboration in addition to technology development collaborations.
Thank you so much.
Dear participants, any other questions? You can raise your hand or either use chat box for. Any more questions? Okay, sir, I think we are done with the questionnaire round also. So shall we go for the next vote of thanks?
Yeah, I think. Fine for me.
So
Ma'am?
vote of
Ma'am?
thanks. Yes, sir.
Ma'am, please give the token of appreciation award virtually to Mr. San
Yeah.
Santosh, sir.
So thank you so much. You have been here and the session was wonderful. Please accept our vote of thanks, both the certificate and the momentum, but we come down physically and meet you for the session. Thank you so much for being here, sir.
Thank you. Thank you very much for the opportunity, madam. Always a pleasure for us to deliver these things. Yeah.
Yeah. Thank you, sir. Now I request Ram Subramanian, sir, to move with the
Okay.
vote of thanks.
It was a wonderful session. We are very fortunate to have Mr. Santosh Sham Koski, Joint Director, CDAC Hyderabad. And we are very lucky to have such smart technology award in the year 2015. Really, it was a great surprise. And sir, it was an excellent lecture, very well planned. And the definition of IoT you started very well. And we enjoyed this lecture. I hope every participant will be getting a lot of input that the role of IoT in agriculture. Thank you very much, sir, for your wonderful presentation. Thank you, sir.
Thank you very much.
Thank you, sir. By this, we want to end the session. Thank you so much. I thank all the participants also, and very good night for everyone. Thank you, sir.
Thank you.
Thank you, sir. Sandeep, sir?
Sir, kindly close the session, sir. Thank you.
Thank you, ma'am.